The minor planet Arrokoth, which the NASA New Horizons probe passed by on New Year's Day 2019, is one of several similarly shaped objects observed in the Kuiper belt beyond Neptune. The object's brightness, as observed through a light curve, was used to determine the dimensions and shape of Oumuamua. When the wider side of Oumuamua was visible, it appeared brighter. The exact stellar system from which Oumuamua originated remains a mystery. However, in 2018, researchers traced Oumuamua's trajectory back to its original route toward the Sun and discovered that it passed close to 4 stars, with the red dwarf star HIP 3757 being its closest encounter. It is possible that Oumuamua originated there or that it has been adrift in space for an extended period. Oumuamua's trajectory was hyperbolic, meaning it approached the Sun at such a high speed that its path could only be minimally influenced by the Sun's gravity. As a result, it did not get captured in a looping orbit but rather continued on a trajectory away from our solar system. Oumuamua was not discovered until over a month later on October 19, 2017, when University of Hawaii astronomer Rob Warrick spotted it in observations made by the asteroid-hunting Pan-STARRS system. At that time, Oumuamua was 21 million miles from Earth, and its closest approach brought it within 15 million miles. It has since been moving away from our solar system, propelled by a gravity boost from the Sun due to its small size and rapid motion away from Earth. The window of opportunity to observe Oumuamua was short, lasting only a few weeks. The Hubble Space Telescope provided the longest observation period by combining data from 2 of the world's largest optical telescopes, the Very Large Telescope in Chile and the Gemini South Telescope. However, even with the finest photos, Oumuamua appeared as nothing more than a tiny speck. Currently, Oumuamua is well beyond Neptune's orbit and is heading towards the constellation Pegasus. It is now whizzing through the Kuiper belt, a ring of frozen objects near the periphery of the solar system. It is no longer visible to our telescopes, and the chances of it returning to Earth are slim. The true nature of Oumuamua remains a matter of speculation. Some have wondered if it could be an alien probe. What we do know is that Oumuamua was an object ejected from a planetary system outside of our solar system when the gravitational forces of roving gas giants pulled it out of its orbit. Prior to the discovery of Oumuamua, astronomers believed that interstellar objects like 2I/Borisov would resemble comets. For a long time, it was assumed that Oumuamua was a dormant comet whose volatiles, such as water, had evaporated over billions of years, either in its original system or while passing by other stars. However, Oumuamua's non-gravitational acceleration was detected by the Hubble Space Telescope as it departed from the Sun. This acceleration is typically observed in comets due to the outgassing of water vapor and dust, which creates a tail and provides an additional boost. Yet, there was no indication that Oumuamua was releasing water or any other volatile substances typically seen in comets. As the first known interstellar object, it provided valuable insights into the nature of other planetary systems. Its peculiar shape and lack of a tail intrigued scientists, leading to various hypotheses about its composition and origins. Oumuamua's trajectory, propelled by a gravity boost from the Sun, took it on a hyperbolic path away from our solar system. Although Oumuamua's true nature remains uncertain, its fleeting visit left us with more questions than answers about the fascinating world of interstellar objects. But we need to understand what this object is before Oumuamua collides with our planet. Now we will look at the best theories to explain what Oumuamua is. What fascinating theories have been used to explain the wild concept of Oumuamua? There are several theories about what Oumuamua could be, each with its own set of arguments and evidence. One theory proposed by Stephen Desch and Alan Jackson from Arizona State University suggests that Oumuamua may be a lump of nitrogen ice that was blown off a Pluto-like body due to a massive impact. This theory is supported by the discovery of regions on Pluto, such as Sputnik Planitia, which are frozen nitrogen lakes. If Oumuamua was made of nitrogen ice, it would have needed an additional boost from the Sun's heat to become visible. Nitrogen gives comets a more reflective appearance, and Oumuamua would have appeared pale due to its small size. Another theory put forth by Daryl Seligman from Cornell University and Jennifer Bergner from Berkeley University suggests that cosmic rays may have reacted with surface ice on Oumuamua while it was in interstellar space, releasing hydrogen gas trapped in amorphous water ice. This theory explains why Oumuamua didn't have a dust tail, as the dust would have remained trapped in the water ice. The heating from the sun would have altered the crystal structure of the ice, allowing the hydrogen to escape at a rate of 0.4 to 28 ounces per second. Astronomers Avi Loeb and Shmuel Bialy from Harvard University propose a more unconventional theory. They suggest that Oumuamua could be an artificial solar-powered spacecraft. They base their theory on the non-gravitational acceleration observed in the object's trajectory, as well as its numerous peculiarities. According to Loeb and Bialy, an artificial origin would explain these observations more satisfactorily than a natural explanation. Determining the exact size and shape of Oumuamua is challenging since astronomers have not been able to obtain a detailed photograph of the object. Instead, they rely on its brightness and their understanding of the reflectivity of asteroids and comets to estimate its size. The absence of a coma or tail surrounding Oumuamua further complicates the identification of its nature. Avi Loeb does not believe that the comet scenario is valid, as outgassing would have altered Oumuamua's rotation period, which has not been observed. He suggests that the apparent movement could be due to the kick that caused Oumuamua to break free from its parent object. Loeb and Bialy propose a novel theory that suggests the observed non-gravitational movement of Oumuamua could be caused by solar radiation pressure. They argue that if Oumuamua is only 0.3 to 0.9 mm thick, it could be a light sail, a structure that uses the kinetic energy of photons to propel itself. They point out that similar technology has already been demonstrated in orbit with missions like Icaros, Nanosail, D2, and Lightsail. According to calculations by Bialy and Loeb, a light sail Oumuamua could survive a long interstellar trip, potentially traveling at least 16,000 light-years from its home system. However, the object's origin remains unknown. While Bialy and Loeb do not assert that Oumuamua is undeniably an extraterrestrial spacecraft, they consider this possibility in high regard. The discovery of Oumuamua was quite remarkable, as it was an anomaly among the objects in our solar system. If Oumuamua is indeed a random member of a larger population of similar objects, its chance discovery suggests that stars in the Milky Way eject trillions of such objects over their lifetimes. This is in contrast to our own solar system, which doesn't shed as many objects as Oumuamua. The object's motion aligns with the kinematic space called the local standard of rest, making it difficult to determine its system of origin. While we may never be able to catch up to Oumuamua using conventional chemical rockets, there is a possibility of getting a closer look at the object. Projects like Breakthrough Starshot aim to launch small robotic probes equipped with sails that can travel at high speeds towards Oumuamua and similar objects. By conducting a full-scale observational blitz, astronomers can gather more data and insights from such objects, which will help us be better prepared for future encounters. Oumuamua's visit has sparked various theories about its nature and origin. While its true identity remains uncertain, the exploration of this interstellar object has provided valuable lessons and inspiration for further astronomical research. By studying objects like Oumuamua more closely, scientists can uncover more about the mysteries of our universe. Where did Oumuamua come from? Scientists are still grappling with the puzzling mystery of the strange cosmic traveler, which has ignited a multitude of questions. While its interstellar nature is undeniable, its origin remains one of the most captivating scientific mysteries of our time. Initially, experts believed that Oumuamua may have hailed from Vega, a brilliantly luminous star in the constellation of Lyra. Vega, known to possess debris disks, presented a plausible source for Oumuamua. If this hypothesis held true, Oumuamua's odyssey to our solar system would have spanned a staggering 600,000 years. However, recent developments have challenged the Vega theory. A shift in trajectory has dispelled the notion that Oumuamua originated from Vega, redirecting our focus to alternative possibilities. The range of potential options is vast, with some suggesting that Oumuamua may have traversed our galaxy for billions of years, traversing a distance of over 20,000 star systems. While this time frame may appear immense, it pales in comparison to the estimated age of our galaxy, which is around 10 billion years old and harbors a staggering 200 billion stars. Astronomers speculate that Oumuamua's encounter with our solar system might mark its inaugural interaction with a newfound star system, given the duration of its cosmic journey. This hypothesis gains support from its passage around the Sun at a velocity akin to neighboring stars. To investigate the origin of Oumuamua, scientists have meticulously retraced its trajectory to a time before it entered our solar system. Corin Baylor-Jones of the Max Planck Institute for Astronomy undertook the arduous task of juxtaposing Oumuamua's path with the prior positions of approximately 7 million stars. By scrutinizing data from the Gaia spacecraft, which has meticulously monitored these stars, Baylor-Jones reconstructed their orbits and sought intersections or resemblances with Oumuamua's trajectory. This exhaustive investigation identified 4 promising candidates, each exhibiting paths closely mirroring Oumuamua's rewound course. While one of these candidates is believed to be Oumuamua's ancestral home, definitively ascertaining its origin remains a complex challenge. During the investigation, Baylor-Jones made a captivating discovery. He found that Oumuamua's trajectory aligned with a region between 1 to 2 Oort cloud radii or 100,000 to 200,000 astronomical units, AU. The encounter velocities between Oumuamua and each of the potential origin candidates were strikingly high, ranging from 6 to 16 miles per hour, posing a perplexing enigma for scientists. Some researchers have posited that Oumuamua could be a planetesimal, a constituent expelled during the formative stages of a planet. However, achieving such elevated ejection velocities solely through encounters with larger planets is highly improbable, though not entirely implausible. Another possibility is that Oumuamua originated from a binary star system, which could account for its substantial velocity. Nevertheless, none of the 4 most promising origin candidates for Oumuamua are binary stars, further adding to the intricacy of the puzzle. The quest to unveil Oumuamua's true origin persists, with the hopeful anticipation that forthcoming Gaia data releases will furnish more insights into this cosmic enigma. Additional data from Gaia will enable astronomers to refine their quest for the celestial Voyager's birthplace, offering further elucidation into the motions of neighboring stars and potentially yielding more conclusive outcomes. What could we do in the event that the Oumuamua space probe returns? In the event that the Oumuamua space probe returns, there are several considerations and challenges to address. Assuming that something extraordinary has occurred, it is worth speculating on what steps humanity should take if the asteroid space probe comes around again. To construct a spacecraft capable of pursuing the probe, a deeper understanding and manipulation of dark energy in the cosmos is necessary. One suggestion is to send a craft after the asteroid probe, but the challenge is formidable. Oumuamua has a hyperbolic excess velocity of 5.5 astronomical units, AU, per year, which means it will be beyond Saturn's orbit within 2 years. This velocity is much faster than any object humanity has ever launched into space. Therefore, the vessel required to pursue Oumuamua would need to be extraordinary. The question arises as to what kind of vessel it should be and how far it would stretch the boundaries of realistic physical theory. Should we board the ship in space, or should we use fuel to leave the gravity of Earth and then prepare for interstellar travel? Additionally, there is the question of the method by which we would travel through space. Solar sails and wormholes are 2 possibilities to consider. However, the concept of wormholes is fraught with several issues. Firstly, they tend to collapse just before someone attempts to pass through them. Secondly, wormholes are believed to connect to other universes, not just distant corners of our own universe. Finally, constructing a wormhole is currently beyond our technological capabilities, and we have limited knowledge of how to achieve it. But that's not all. The return of Oumuamua would undoubtedly ignite a frenzy of scientific excitement and curiosity. Its re-entry into our solar system would offer a second chance for researchers to study this intriguing celestial object up close. One potential course of action would be to dispatch a fleet of advanced space probes to rendezvous with Oumuamua, equipped with cutting-edge instruments and sensors designed to unravel its mysteries. We could envision a scenario where a swarm of miniaturized spacecraft, equipped with artificial intelligence and advanced propulsion systems, are sent to intercept Oumuamua. These miniature probes, akin to nanobots, would be capable of autonomously gathering vast amounts of data about Oumuamua's composition, structure, and origin. They could employ novel imaging techniques to capture high-resolution images of the object's surface, revealing intricate details and potential clues about its journey through the cosmos. However, such a mission would not be without its challenges. The first hurdle would be the need for rapid response. Oumuamua's return would likely be unexpected and brief, leaving little time for the development and launch of a traditional space mission. The miniaturized probe concept could mitigate this challenge, as the small size and streamlined design would allow for quick production and deployment. Another obstacle lies in the immense distances involved. Oumuamua's return would likely occur at an extraordinary distance from Earth. Overcoming this obstacle would require breakthroughs in propulsion technology, enabling the miniature probes to traverse vast interstellar distances within a reasonable timeframe. Alternatively, we could consider utilizing existing spacecraft or even leveraging solar sails, which harness the pressure of sunlight, to propel the probes towards Oumuamua. Once the miniature probes reach Oumuamua, a new set of challenges awaits. The object's irregular shape, unusual rotation, and potential surface roughness could complicate the probe's ability to establish a stable connection. Overcoming these challenges may involve developing advanced docking or anchoring mechanisms, capable of securing the probes to Oumuamua's surface or utilizing advanced robotic arms to maintain a steady position. Additionally, investigating Oumuamua's origin and nature would require innovative scientific techniques. For instance, researchers could utilize laser-based spectroscopy to analyze the object's chemical composition or employ deep learning algorithms to decipher patterns and anomalies within its structure. These approaches would require significant computational power and advanced data processing techniques to derive meaningful insights from the vast amounts of data collected. Moreover, the return of Oumuamua would raise profound ethical and philosophical questions. Should we intervene with an object that may hold insights into the mysteries of the universe, or should we leave it undisturbed as a pristine artifact? These dilemmas would require careful consideration and international collaboration to ensure responsible and respectful exploration.